In today's video, we will be looking at the finite element analysis of a cantilever beam subjected to a point load. The topics are as follows. First is the problem definition. Then we will use the analytical method to solve the problem. Then we will solve the problem by the FEA Matrix method. And after that, we will simulate the problem in the Ansys Workbench and compare the results. The problem is as follows. A cantilever beam is subject to a point load at the free end of 5,000 newtons. The beam has a square cross-section with sides of 100 millimeters. The length of the beam is 1 meter, and the material has a Young's modulus of 200 gigapascal. The analytical method to solve the problem is as follows. We derive using the double integration method, and using the boundary conditions, we find the function of slope and deflection. From the function, we can find the maximum values of slope and deflection, which are shown on the slide. Using the equilibrium condition, we find the reaction force and moment at the fixed support. And due to loading, the bending stress and shear are induced in the beam. The maximum value of stress are calculated. Also, the stress distribution is shown on the slide. For ductile material, the most reliable failure theory is von Mises theory, which is based on the distortion energy in the material. The general stress configuration and how calculate the von Mises stress is shown from this. We'll calculate the von Mises stress for our problem. Similarly, for maximum shear stress theory, we calculate the maximum shear stress in the beam. The theory of failure helps to identify that for given loading condition, will material fail or not? And the value of corresponding theory is comparing with material properties. If higher than material will fail. The governing equation for beams is shown, and using the finite element method and boundary conditions, a general elemental matrix can be obtained. For this problem, we will consider one element. We write the elemental matrix for element by applying the boundary conditions, which are as follows. Since node 1 is a fixed support, both the theta and vertical deflection will be 0. And at node 1, unknowns are force and moment. At node 2, we have force equal to 5,000 newtons in a downward direction with 0 moment, and the unknowns are theta and vertical deflection B. We obtain the equation, which is solved for finding the unknown. From the obtained unknown, the force and moment are also calculated. And now we move to the Ansys Workbench for the simulation. Drag and drop the static structure into the project. Go to engineering data and edit the material properties for this problem. The default value matches the given data. Now open Design Modeler. Change the units. Choose the XY plane and draw a line. And give the dimension as the length of the beam. And now go to the concept, choose the line from sketches option, select the sketch, and change the operation to add frozen. Now to add the cross-section, go to concept, choose cross-section, and select rectangle. Give the dimension to the cross-section as per the given data. Apply the cross-section to the line body. For that, select the line body and choose the cross-section. And then click on Generate. And the geometry part is finished. And we will go to Ansys Mechanical for the analysis. First, check the material assignment by going into Geometry. Generate the default mesh. For the boundary condition, apply the fixed support by inserting fixed support and select the point. Similarly, apply the force in the negative y direction by inserting force, choosing a component, give the value now click on Solve to find out the deflection, insert deformation in that select total deformation. For the force reaction, go to Insert, choose Probe, and add force reaction, choosing it fixed support. Similarly, add the moment reaction at the fixed support. Note down the maximum value for each of the parameters. To compute the maximum bending stress, insert beam tool. Delete all the stress and insert max bending. Beam gives accurate result, but the distribution is not correct. To get correct distribution with enable beam section result, and insert normal stress in direction of length of beam. The normal stress gives accurate value plus the distribution. Similarly, insert shear stress. But it shows 0 value. Similar steps are repeated for the equivalent von Mises stress and maximum shear stress. For displacement versus length, graph in line body, insert directional deformation, and select the edge and apply. Right-click on directional deformation and click on Convert to Path Result, evaluate the result. From this graph, we will calculate the slope using curve fitting. You can also see the shear force and bending moment diagram. Insert total shear moment diagram from the result and select the edge, evaluate the result. Save the project. The result is tabulated. The deflection force and moment reactions of ANSYS match the analytical and FEA Matrix methods. And the bending stress also matches with theory, but shear stress is 0 in case of ANSYS, which result in inaccurate equivalent von Mises stress and maximum shear stress. Note that for result purposes, we took the absolute value. The references are as follows. Did you think about this? We have discussed about theories of failure, which theory is applicable to this simple cantilever. Did you think about shear stress induced in beam and why it was showing 0 in ANSYS? That's all for today's video. Thank you.